First, I would like to thank the organizers for having me this workshop. And today I'm going to talk about the mineralogical model of the lower mantle based on our recent sound velocity data obtained under very high pressure conditions. And before starting my talk, I would like to thank to my collaborators listed here for their great contribution of this study. So, first of all, as you all know, it is widely accepted that at least the upper part of the upper mantle has chemical, peridotic bulk chemical composition based on the geochemical and petrological considerations. On the other hand, a number of possible compositional models for the lower mantle have been proposed to satisfy the seismological observations ranging from peridotic to more silica-rich compositions like chondritic mantle. However, this issue still remains controversial due to the lack of conclusive experimental evidences. So as we all know, the seismic wave observations are essential keys to understand the mineralogical model of the deep mantle. And recent seismic observations have found some anomalous seismic wave observation in the deep mantle, suggesting the large-scale chemical or thermal heterogeneity in the lower mantle, such as large low shear wave velocity provinces and ultra-low velocity zones. So basically, in order to detail modeling of the lower mantle, we should think about this complicated seismic heterogeneity, but to a faster approximation, the 1D global seismological model in the Earth's interior, such as PREM, provides us one of the strongest constraints on the deep mantle mineralogy. And obviously, the reliable determination of the reliable sound wave velocity of the Earth's deep materials and relevant high pressure and high temperature conditions is essentially important to reconstruct the mantle model of the lower mantle. However, it has been a great challenge to obtain the sound wave velocity of the Earth's deep materials and the relevant and extremely high pressure condition in the Earth's interior. So in order to put stronger constraints on the lower mantle mineralogy, we basically need to clarify the effect of pressure and chemistry and temperature on the sound wave velocity of the lower mantle constituent minerals, like 130 GPa and something like iron and aluminum, and high temperature conditions above 2000 Kelvin. However, previous sound wave velocity measurement has been made only up to 9 GPa by ultrasonic measurement, and which is actually far below the thermodynamic stability field of the MgSO3 perovskite. And according to the previous lower pressure sound wave velocity measurement below 9 GPa, the seismic shear wave velocity of perovskite phase is relatively higher and steeper than that of PREM profile as shown here, suggesting that lower mantle is more like a peridotic composition. However, as I mentioned, the their work were performed under very low pressure conditions. So there might be have some large uncertainties in high pressure conditions. So in order to overcome the experimental difficulties, especially for high pressure sound wave velocity measurement, we have developed high pressure Boolean scattering spectroscopy combined with diamond anvil cell high pressure apparatus in collaboration with Professor J. Bass at the University of Illinois, which is one of the most promising ways to detect the sound wave velocities, especially for the transparent materials and extremely high pressure conditions. And I don't want to go into detail on the system, but this newly developed system enables us to drastically extend the upper limit of the pressure for the sound wave velocity measurements. And with this system, we first determine the shear wave velocity of perovskite under lower mantle pressure conditions. And these are the results of the shear wave velocity profiles of pure MgSiO3 perovskite as a function of pressure about 100 gigapascals. And these data were fitted to finite strain equations, and we obtained the best fit values of shear modulus and also its pressure derivatives, as shown here. And as you can see, the previous experimental work has significantly higher G prime value than our studies. However, as I mentioned before, these works were performed at a very low pressure condition, below 9 GPa. Therefore, the huge extrapolation to the high pressure condition may again result in the highly uncertain estimates. So with this system, we have so far succeeded to measure the shear wave velocity of pure MgSiO3 perovskite to about 100 gigapascal, and pure MgO to a pressure about 130 GPa, and also pure MgSiO3 post-perovskite phase to about 172 GPa. And in terms of high pressure, we have achieved the shear wave velocity measurement above 200 gigapascals on the silicate glass, as shown here. So actually, these observations, in fact, provide the very critical information on the lower mantle mineralogy. However, in order to give a more precise constraint on the lower mantle mineralogy, we need to clarify not only the effect of pressure, but also the effect of chemistry and also the effect of temperature as well on the sound wave velocity of the lower mantle phases. So the effect of chemical composition in the lower mantle minerals can primarily fall into two major elements of iron and aluminum. And in the lower mantle, the ferropericlase and also the silicate perovskite is believed to be the primary carriers for the iron and aluminum, respectively. Although such chemical impurities were reported to have strong effect on the physical property for both phases, the high-pressure sound wave velocity data are still limited to very lower pressure conditions. In order to clarify these issues, we have conducted the shear wave velocity measurement of ferropericlase with 8 mol% iron up to a pressure of 120 gigapascal, and also the aluminous perovskite with 4% alumina up to a pressure of 124 gigapascals. using newly developed Brilliant scattering system, installed at Japanese synchrotron facility of Spring 8, as shown here. And I will touch upon this system a little bit in detail later. So this is a representative low Brilliant spectra of the ferropheric rays at 86 GPa. And as you can see, the very sharp peaks from the sample can be observed, even at very high pressure conditions. And this is a result of the shear wave velocity profile of ferropheric rays together with the previous reports. And since we have observed the very discontinuous feature around 50 gigapascals, we tentatively put the possible spin transition pressure as shown this shade. And we found that the shear wave velocity trend of the low spin state becomes slightly gentler than that of high spin state labeled by blue line. In addition, our shear wave velocity data are very consistent with recent Brilliant scattering measurement by Markert et al. 2009. However, we did not see any clear evidence of the elastic softening across the spin transition that Crowhurst et al. 2008 previously reported. So based on the finite strength fits, we determined the compositional dependent of the ion on the pressure derivatives of shear modulus, both for high spin and low spin, like that. And with those trends, we estimated the representative mantle values of the pressure derivatives of the shear modulus for both high spin and low spin, as shown as these stars. Now let's look at the aluminous perovskite. And in the experiment for the aluminous perovskite, the aluminous perovskite was synthesized in situ at high pressure condition in the diamond anvil cell with laser heating from the gel starting materials. And we obtained very sharp X-ray diffraction pattern from the sample as shown here. And these are very sharp peaks from the perovskite. And this means that we obtained that very fine-grained polycrystalline perovskite samples. So this is a representative Brilliant spectrum of the aluminous perovskite at 95 GPa. And you can easily recognize the very sharp peaks from the transverse acoustic mode from the sample here. So this is a result of the shear wave velocity profile for aluminous perovskite labeled by red, and also together with pure MgSiO3 perovskite labeled by blue. As you can see this figure, the effect of alumina seems to be very small. And the result demonstrates that the slightly smaller shear modulus relative to the pure MgSiO3 perovskite. However, the pressure derivatives of the shear modulus is almost the same as pure MgSiO3. This means that the effect of alumina is very small in terms of the elasticity. So now we have sound velocity data of the lower mantle constituent minerals and the relevant pressure conditions, including the compositional effect in the system of MgO, SiO2, FeO, and aluminum, which enable us to put stronger constraint on the mineralogical model of the lower mantle. So for the modeling, we calculated the shear wave velocity profiles along the representative lower mantle geotherms in the chemical composition system of MgO, SiO2, FeO, and aluminum. And the calculation was made using the formalism proposed by Stix through 2005. And as you know, there are several geothermal models for the lower mantle. This is huge scattered. And in this modeling, we adopted two extreme cases, one for full mantle convection model, and the other for layered mantle convection model, as shown here. And here we show the result, calculated shear wave velocity profiles for the perovskite labeled by blue and ferropericles labeled by black, together with the PREM labeled indicated by white circles. So as you can see, the shear wave profile of perovskite itself is almost identical to the PREM already. And the PREM profile can be best fitted by the model with 95 volume percent of perovskite, as shown these red lines. On the other hand, the PREM peridotic mantle model, shown as this green line, does not match the PREM, having about 3% lower velocity, which means that the full mantle convection geothermal model is no longer valid. Then we apply the layered geothermal model for the layered mantle convection and calculated the shear wave velocity as in exactly same as the previous one. And we found that the shear wave velocity profiles of the PREM can be best fitted only by the perovskite, as shown here. To summarize our modeling, the result indicates that the conventional peridotic lower mantle model is not compatible with the PREM, and strongly suggests that the lower mantle is dominated by the perovskite. Since the upper mantle is believed to have a peridotic chemical composition, as I mentioned before, the perovskitic lower mantle is silica-rich in comparison with the upper mantle, implying that the chemical stratification between upper and lower mantle. So the different chemical composition between upper and lower mantle could be a consequence of the fractional crystallization within the magma ocean in early Earth. And probably the primordial chemical stratification could be preserved until present day. This is a very okay. But this is a very problematic because, as you know, there are significant arguments in the geodynamical society that the layered mantle convection is much less preferred based on the present-day characteristic and also the long-term geological evolution of the Earth. So we need to think more about these issues from the geodynamical point of view. So now I'm go back to the experimental issues again. And obviously, what we should do next is to clarify the effect of temperature. So in order to clarify this temperature issue, we have further developed the sound wave velocity measurement system at the spring rate. And this figure shows the schematic drawing of the system. And this system basically composed of three optical components of Boolean scattering and X-ray diffraction and laser heating, so which enable us to get shear wave velocity or sound wave velocity under relevant condition of the lower mantle, which means that a higher pressure and also high temperature condition. So with this system, we have so far succeeded to obtain the X-ray diffraction pattern and high pressure and high temperature condition, and also the Boolean spectrum like this. But the high temperature data still have large uncertainties due to the experimental difficulties and also the experimental configurations, so which apparently needs to be improved in the near future. And this is an ongoing project for us. So here I put the remaining experimental issues and the problem to be solved. And to better understanding the lower mantle mineralogy, we definitely address the effect of spin transition of iron in perovskite phase, and also the combined effect of aluminum and also iron on the elasticity of the perovskite phase. And as I mentioned, the data quality at high temperature data has to be improved by the development of the new techniques. And this is a summary of these studies, and we have determined the sound velocities of pure MgSiO3 perovskite, MgO, and iron-bearing ferropericlase, and aluminous perovskite under lower mantle pressure conditions. And mineralogical modeling using obtained results strongly indicate that the perovskitic lower mantle. And the development of new techniques enable us to explore the sound velocities under lower mantle conditions. Thank you for your attention.